Hey everyone, in this lesson we are going to be looking at queues and what they are and how we can use them in our games. So I have a little example right here which is sort of just an abstract view of what you may have for your game in terms of a command system. Okay, if you've ever played The Sims or some RTS games, you might be familiar with the idea of giving commands to units, giving commands to the player. And we can stack those commands up so that once one is complete, they can move on to the next. So for example, let's just press play and we can say, okay, we want them to gather wood, we then want them to hunt, we then want them to build, and then do some scouting. Well, we can then run the command, and as you can see, it will gather wood, it will then hunt, then build, then scout. Okay, so basically a queue is a list of things. It can be pretty much anything you want. We can add stuff to a queue, and then we can basically remove something from the queue at the start. So it's basically first in, first serve. Very similar to a real life queue. If you're lining up to purchase something, for example, you would, line up one person at a time, and then the person at the front of the line would then be served, and they then move along. Okay, so let's hop over into our script now and have a look at how we can set this up. Okay, so here in my script, I've already got a couple functions already created ahead of time, just so that I don't have to reconnect them to the buttons. But pretty much we have a add command button function, which gets called when we click on a command button on the UI. We then have run next command, which runs whatever command is up next, and then an update function to basically update the UI text. So what I'm going to do is first of all create myself a queue. So I'm going to create a private variable. I'm going to go queue. And then in angled brackets, we need to enter in the queue data type, which is going to be string. Give it a name, we'll call it commands, and we'll initialize it like so. Now, a queue is in the same family as, for example, a list and a dictionary, okay? A queue is what is known as a collection. Now, when working with lists inside of C#, a list is basically a variable which can hold many different elements. We can add stuff to a list, we can remove stuff from a list, we can access specific elements of a list by getting its index number and modifying it that way. Whereas with a queue, this is a much more simplified version. You can think of it that way, okay? A much more simplified version of a list which has a very specific use case. Okay, with a queue, we can add stuff to the queue and basically then remove stuff from the queue. Okay, so it's basically, like I said before, first in, first serve. You add a bunch of stuff to the queue, the thing that was added first will be the first one to be removed. So how do we add something to our queue? Well, down here inside of the add command function, what we're going to do is we are going to call the enqueue function. So we'll go commands.enqueue like so. And then pretty much we can then give it a element to add, such as command. Okay, this is very similar to the add command for a list. We are basically adding a new element to this collection, like so. And that is pretty much it for adding stuff. Now, in terms of removing stuff from a queue, we need to call the dequeue function. So if we go down here to the run next command, what we can then do is just go commands.dequeue. And what this will do is this is going to remove the first element of our queue, okay? The thing that has been there the longest, it's going to remove it. But it also returns it to us as well so that we can use it because, there's no real point if we are adding stuff and removing them without ever being able to use it. So we can store this dequeue. As you can see, it returns a string, and I'm going to store it in a string variable. So I'll create a string, we'll just call this one CMD, and this is going to be equal to command.dequeue. So this is going to take the first thing at the front of the queue, store it inside this string variable, and then remove it from the collection here. Then what we can do is just go debug.log, and we can just log that to the console like so, okay? Now what we can do is go back into the editor here, okay? We can then press play. And the functionality we have so far is what we can do. We can go gather wood, gather stone, and hunt. Now we should see in the console here, this queue be dequeued. So if I go run next command, there you see gather wood. That was the first thing we added to the queue. Then we have gather stone, and then finally we have hunt. So we're basically adding stuff to the queue and then removing it from the front. Now if I click run next command again and try and dequeue, we're going to have an error, and that is because, as you can see here, the queue is empty. So a quick way of debugging this error to make sure that this doesn't occur during your proper runtime is we can add a little if statement at the top of our run next command function. And in here, we're just going to go if command.count equals 0, then we are just going to return, okay? We're not going to do anything if we have no commands left. So we're just going to skip over this. And we can even add in a little debug message here. We can go debug.log. We can just go no commands to run, okay? Just letting the user know that there's no more commands for them to run. Okay, so we have that all set up. Now, what I'm going to do then is just go down to the update queued commands text, and I'm just going to make it so that our queued commands get displayed inside of that little text field. So for this, I'm just going to go up to the top, go using TM Pro because we want to create a Text Mesh Pro reference here. Create a serialized field, a private TMP underscore text, call this commands text. And then down here in the update queued commands text, we are first going to set the text to be equal to string.empty. And then we are going to loop through each of our queued elements. So we're going to go for each. It's of type string, command, in, commands. And then pretty much we're just going to go commands, text, dot text, plus equals, command, and then we'll also add a little comma at the end as well, just to separate them. Okay, like so. And then finally, we want to call this function whenever we run a command and whenever we add a command to our queue. All right, so we can save that, go back inside of the editor here. I'm just going to quickly connect up that text to the property here, press play. And now when we add our commands, we can see them be displayed at the top of the screen here. So we want to gather wood. We then want to maybe build a couple times, do some fishing, scout. And yeah, now when I run the next command, you can see that the first one is gather wood. So that is going to be ran. We then have build. We then have build again. We then have fish. And finally, scout. And if I keep clicking the button, you can see that little debug message that we added gets called here. So no commands to run. So yeah, a queue is a very specific collection with very specific use case. But generally, if you are working on a game that has this sort of system where you might want to queue up commands or queue up certain events to happen, queues are generally a good thing to use, as you probably don't need the complexity of something like a list or a dictionary or an array, and queues may just be what you need. So yeah, now in the future, whenever you run into a system or an issue where something like this comes in handy, you can always know that you can rely on using queues. Hey everyone, in this lesson, we are going to be looking at interfaces inside of C# and Unity. So what I have right here is a little scene, and what I want to do is make it so that whenever I click on one of these objects, whatever it is meant to do happens. So for example, our cube right here, this has a color change script attached to it, and we have a function called change color, which basically gives it a random color. Then we have our ball, and this ball, what I want it to do when I click on it is I want it to bounce, and I have this bounce function in its own script right here, which just adds force upwards. And then finally, we have this door. And inside of the door script, we have a function which basically just opens or closes the door right here. Now, what I want to do is make it so that whenever I click on one of these objects, that happens. So how could we go about doing that? Well, I've gone ahead and also set up an interact controller script, and all we are doing here is checking to see when we have clicked on our, checking to see when we click our left mouse button. We then call the try interact function, which basically just shoots a raycast from our mouse pointer to whatever we hit. And then if we hit something, we can do something, okay? Now, the way we might go about this is by checking to see, okay, is the object we hit a color changer? If so, call the change color function. Otherwise, if it is a ball class, then call the bounce function, or if it is a door, call the use function, okay? We could do that, but you know, that would get convoluted very quickly. And if we had, for example, 100 different interactable items, then we would just have hundreds of lines of code checking to see, was this a ball, was this a door, was it an item, was it a so-and-so. So instead what we can do is use an interface to basically connect everything up very nicely. Now, an interface is basically a collection of different function signatures and properties that we can assign or implement into a class. Now, let's just go ahead and create the interface first up so that we can see what it is, and then from there learn how we can use it. So to create an interface, what I'm going to do is I'm going to go to my project browser here, and I'm going to create a brand new C# script. Now I'm going to call this one iInteractable, okay? Now generally with interfaces, the general practice is to have an interface start with an I, a capital I. You don't have to, of course, you can call your interface whatever you want, but I'm going to call it iInteractable since that's the general practice. Now, with an interface, we aren't going to be using the class or any of these using, so I'm going to go ahead and actually just delete everything inside of this script file, so it is empty. And to define an interface, we first of all need to write down public interface, okay? Similar to it as if we were creating a class. We then give the interface name, which is iInteractable. Then we want to add in our squiggly brackets right here, okay? Now we have defined an interface. But for this to actually be useful, we are going to then assign some function signatures. And this is basically, we aren't really creating a function, but we are rather creating a list of functions that must be created for every class that uses this interface, okay? So we are going to have one function, and that is going to be the interact function. So I'm going to go void interact, okay? Parentheses, and end that off with a semicolon, okay? So what we are doing here is not creating a function, but rather we are creating a function signature. We are telling this interface that this here is what needs to be implemented in whatever class uses this interface, okay? And if you did want parameters to be sent over, you can as well. So for interact, you might have a string for message or something like that. You can, of course, add parameters, and you can add many more functions down here if you wish. And you can also customize the return type as well. We just have it on void for now, okay? So we have our iInteractable interface. So how do we implement it? Well, let's go over to our color changer script right here. Now, we wanted to make it so that whenever we click on this color changer object, we have a random color assigned to it. Well, first of all, let's implement the interface. To do that, we are going to go up to where we have the class definition here and the monobehavior parent class. We are then going to add a comma and implement iInterface like so, okay? Now, you'll notice that after we do that, we again error. Okay, we get this red squiggly line underneath iInterface, and that is because, as you can see, it says color changer does not implement interface member interact function. So what we need to do is we need to create a function that is pretty much matching this function signature. So it needs to be a function called interact. So if we go over to our color changer, we can create a new public void interact, like so, and the error goes away. And then what we can do is go down here and just copy and paste this line of code into the interact function right here. So now we have a function called interact, which will change this color's material, which will change this material's color. Now, the great thing about interfaces is that we don't actually need to know what class this is. Okay, typically, if you're going to call a function, you need to know what, class the object is. You need to access that object, identify what type of class it is in order to call a function or access a variable. Whereas with an interface, we are not calling this interact function via the class, but rather through the interface. So what this means is that we only need to know if this object has an iInteractable interface in order to call this function right here. So let's go ahead and set that up right now. If we go over to our interact controller, down here where we are raycasting and detecting an object underneath our mouse cursor, we are going to see if that object has the iInteractable interface. So to do this, we can go if hit.transform.getComponent iInteractable, okay, and getting the interactable is the same as just getting a class. We just use the getComponent function. So if this is not equal to null, so if this object does indeed have an iInteractable interface, then we are going to go hit.transform.getComponent iInteractable and you see here in our list of functions we have the interact function that we can call. And there we go. That is all we need to do. So we can save this, we can return to Unity, and now when I click on this cube right here, we should see that it changes color. And that is because our mouse cursor is looking to see not if this is a color changer object, or if this is a ball, or if this is a door. All it's doing is checking to see if the object we are clicking on has the eye interactable interface, and if so, we are calling that linked interact function. So let's go ahead and do the same thing for the ball and for the door. So I'm going to go to our ball script here. We're going to add in the eye interactable interface. Now, if you do have many functions that your interface has, it might be a bit of a pain to go through writing them all down, switching back to the interface to make sure that you have all the correct function definitions. You can click on the interface here, hold down Alt, press Enter, and then press Enter again to implement the interface. And what that's going to do is that's going to create a brand new function down here. And what we're going to do then is we are just going to copy the code that we want to put inside of this function and replace the exception here that gets added by default. There we go. We can then delete the bounce function. And now ball is implementing the eye interactable interface, which is linked to the interact function right here. Same thing for door. We'll go over to door, add that in, eye interactable. And let's just go ahead and actually just rename this function to make it a bit easier. So interact. There we go. And the error will go away and everything is linked up. So we can save that, return back to the project, press play, and now we can click on all these objects here to change the color, to bounce the ball, and to open the door. And the great thing about this is that our mouse cursor, our interact controller, doesn't care what class the cube is, doesn't care what class the ball is, doesn't care what class the door is. Okay, the class is irrelevant in this case. Rather, it is just checking to see if it has the eye interactable interface. So using interfaces in game development is something that is very handy, and if you understand what they are and how they work, certain things of your game development journey are just going to be much easier. Like in this case right here with an interaction system. Pretty much, if you have a game where you might need to pick up items, interact with doors, pull levers, you're not going to be checking to see, oh, is this thing I'm interacting with a lever? Is this an item? Is this a door? Your interact controller isn't going to be worrying about that. All it's going to be looking for is whether or not that object has implemented the eye interactable interface or whatever other interface that you want to implement. And then from there, it is just going to call its respective linked function. Okay, so I have a bit of a problem with my code right here. So what I'm trying to do is set up a script so that over time at the start of the game, the intensity of my directional light goes from 1 to 0, okay? And we're trying to do that over time in around 1 second. So attached to my directional light here, I have a script called light dimmer. And if we open up this light dimmer script, you'll see here we have a variable for our sun. And in the start function, we are calling a coroutine called fade in sun. And basically what this does is it first of all sets our sun intensity to be 0. And then over time through a while loop, we are transitioning that from 0 to 1, okay? Now, the issue comes with this error that we are getting in the console, okay? It is basically saying that the fade in sun, not all code paths return a value, okay? So we're getting an error. We are getting a red line underneath the fade in sun coroutine name right here. So have a go at trying to figure out what is causing this issue and how we can solve it, okay? I'd recommend, if you're having a bit of trouble, check out the Unity documentation for coroutines, as that might be able to provide some information. So have a go at that, and we'll be right back to see how it's done. Okay, so how can we solve this error? Well, if we go over into our light dimmer script, the first thing we need to note is that this is a coroutine function, and a coroutine function basically means that we have the ability to pause the execution of this function at any time. And the way a coroutine works is we kind of have to do that because right now we are not pausing or holding off on this function whatsoever. So essentially what we are doing here is trying to run all of this code in a single frame. Whereas the reason we're using a coroutine is so that we can have this while loop iterate each frame of our game rather than all within one frame. So what we need to do is inside of this while loop, after we adjust the sun intensity a bit here, we have to go to a new line and add in the line of code which reads yield return null, okay? Now, if we save that, you'll see that the error on the name goes away. And the reason why is because before, if we did not have that, then like I said, we were trying to basically run this entire while loop in a single frame. So from one frame to the other, the sun will be an intensity of 0 to 1, okay, or basically snap. Whereas now, we are giving it a command to basically pause the function for a frame, okay? And we're basically telling it, once it reaches this line of code, we want you to hold off for the rest of the frame and then continue on the next frame. So you can imagine on frame 1, the while loop begins, we adjust the sun intensity a little bit, we wait a frame, and then we keep going through this while loop until the intensity reaches 1. Then the while loop is complete and we are finished. So we can save this, we can then go back into our scene, and you should see that the console error is now gone. We can then make sure to give it the light property here, and if I press play, keep an eye on the intensity property here of our light, and what you should see is that it goes from 0 to 1. And there you go. So it went from 0 to 1, and that is pretty much the script complete. So once again, if you are using coroutines, you need to make sure that you are using them correctly, okay? So in our case here, yield return null, we are basically pausing the function for a frame. Alternatively, you could also use another line here, which is something like yield return new wait 4 seconds, and we can pause the function not for a frame, but for a specific amount of seconds. So let's just say we want to pause it for 0.1 seconds each iteration of the loop, okay? So if we go back and press play, you should see that the intensity is going to change a lot slower now, because instead of waiting just a frame, we are waiting 0.1 seconds between every iteration of that loop. And of course, it's going to take far longer. And this is a common issue when working with coroutines inside of Unity. Now, I do recommend checking up the documentation on coroutines, as it will give you a lot more information about the different ways that you can pause your functions and utilize coroutines to their fullest extent. So thanks for watching. Hey everyone, in this lesson we are going to go over the concept of actually baking your lighting inside of Unity. Now, when it comes to performance impacts inside of Unity, especially in 3D games, lighting is one of the major factors that contribute. And when it comes down to lighting, you have two choices. You have real-time lighting and you have baked lighting. Real-time lighting is what is enabled by default, and this basically means that the lighting is calculated every single frame. So if you have an object moving around, it will have a shadow that is tracking it around, and every other object is going to have its shadows, its lighting, the intensity, and all of that calculated every single frame. Now, that's really great if you want to have waving trees, if you want to have players that can run around and have their shadows being displayed. But when it comes to having more complex lighting, such as having lighting bouncing off various different objects and having better performance, that is where baked lighting comes in. And baked lighting is lighting that is calculated by us, the developers, before people play the game. And it bakes it into the textures known as a light map, which is basically a blanket that is put over everything in the scene with all the lighting data and information already pre-applied. So realistically, it's just rendering a texture when we play the game rather than calculating and displaying the lighting every frame. And baking your real-time lighting can actually have the biggest performance increase if you are using a 3D scene, and the more complex your 3D scene is, the more performance you should see from baking your lighting. Now, baked lighting isn't good in all circumstances. Again, if you do want your shadows to be updated as you're running around, real-time lighting may be better for that. So in that case, you can use something such as a mixed light, for example. So you can bake your buildings, your terrain, you can bake your trees and all that. All the objects that aren't going to move in your scene, you can have baked lighting for that, and have real-time lighting for stuff such as the players, the enemies, and everything that is going to be moving around and dynamic. So how do we go about actually setting up baked lighting? Well, if we select our directional light here, and this is just a basic scene that I created just to demonstrate this. On our directional light, you'll see that where it says mode, it is currently set to real time. If we select this, we can choose between real time, which is updating the shadows and lighting every frame, mixed, which is a mix of both real time and baked being it's going to generate the light map and then apply it to our scene when we play the game, so the lighting is pre-calculated. Okay, so right now on real-time lighting, now let's just say we want to go ahead and start baking this lighting. Well, the first thing we need to do is not switch it over to baked. Instead, we need to define which objects we want to include in the baking process. So here I have a drop down of all the various in-game objects just stored under a empty game object right here. And what I'm going to do is I'm going to select all of the game objects I want to include in the baking, so the ground and all these other cubes here. And inside of the inspector, you'll see that we have a checkbox here for whether or not this object is going to be static. So let's enable that right there. And what static means is basically once this game is playing, we cannot move these objects around. They are static. They are built into the scene and pretty much we can't rotate them, move them, or scale them, okay? Okay, so now that we've made these objects static, we can actually begin the process of baking our lighting. So I'm going to select our directional light right here, and I'm going to change the mode from real time to baked. Nothing has really happened. We don't really have anything happening right now. So what we need to do is go to the lighting settings window. And to do that, we can go down to the bottom right corner of our screen and click on this auto generate lighting button down here. This is going to open up the lighting window, and in here is where we can set up our baked lighting. So first of all, if you don't have a lighting settings here set, you can click on new lighting settings. That's going to generate a new lighting settings asset for you, and then you can start editing it here. So the first thing we want to do is scroll down to where we have the light mapping settings, as this is where we are going to define all the various different settings and options when it comes to light baking. First of all, we have the light mapper, and this is basically how we are going to generate our light maps. Now, by default, this is on progressive CPU, meaning that the light baking is going to take place over on your processor. And then we also have progressive GPU. Now, if you do have a pretty good graphics card, I recommend selecting progressive GPU, as this is going to greatly decrease the time it takes to bake. As the larger your scene is, the longer it's going to take to actually bake the lighting, and it can take some time. So I'm going to personally select progressive GPU. Now, if you are on a fairly low-end computer, then you probably should select progressive CPU. Although, if you do know that you have a pretty good GPU, if you're on a gaming computer, for example, then select progressive GPU. Okay, now down here we have direct samples, indirect samples, and environment samples. What these are basically when we are generating our light map, we need to take samples around the scene to figure out the intensity of the lighting, the shadows, pretty much everything in order to determine how the light is going to behave. Because with light, it comes out from the light source, such as our directional light here, and it can bounce off objects. So if we have a light bouncing off the green floor, for example, it can then reflect up onto one of the pillars right here and leave a little bit of green lighting on it when it bounces off. You know, this is what we can do with baked lighting, and with real-time lighting, light bouncing isn't really possible. So, direct samples, indirect samples, and environment samples, the higher these numbers are, then the better your actual light map will look. Although, when you do increase these values, it does take longer to render, as it does need to do more samples. So I recommend just keep it on the default for now. If you do create a much larger scene and you do want to get more in depth into light baking, then you can of course do much more research on what each of these individual aspects are and tweak them to your liking. As when it comes down to lighting, there is no one solution for all projects, as each scene has its own specific lighting settings which looks best for it, okay? Apart from these, we can go down to where it says bounces. This basically determines how many light bounces each ray is going to do. I'm just going to keep it on 2 for now. Light map resolution, this is going to be how many texels per unit. So every Unity unit, what is the resolution going to be? Okay, think of it as pixels on an image. Think of this, how many sort of pixels of lighting we're going to have. So how high resolution do you want the lighting to be, the shadows to be? We're going to keep it on 40 for now, which is the default. Max light map size, it's going to be 1024. Again, if you do want to increase the resolution and the complexity of your light map, you can increase this number, although we're going to keep this at the defaults. And ambient occlusion, which is basically adding in tiny little micro shadows where two objects intersect, as in real life, if you do look at objects that are sitting on top of each other, you can see a slight little shadow where they intersect or where they touch. So we can select that if we do want to have ambient occlusion included. And apart from that, we can just go ahead and click the generate lighting button down here. I'm going to dock my lighting window over in the inspector here. And down at the bottom right, you can see we have a bar that is going to begin going through each of the various different processes in order to bake the lighting. And in our scene view here, you can also see it is going ahead, it's doing all the calculations, and depending on the size and complexity of your scene, it can take some time. Although since this is quite a basic scene, we are pretty much complete right now. And here we go, this is our baked scene, and it looks very similar to the previous one where we had real-time lighting. Although if we look around, you'll see that you do have some sort of artifacting and sort of low resolution looks to this. And this is just due to the fact that we have a lower light map resolution that can be increased. We can increase the direct samples, the indirect samples to get rid of this. Although when it does come down to generating light maps, you will always have these sort of artifacts compared to real-time lighting. Although on the pros side of thing, you do now have much greater performance, and it also allows for light balances and more complex lighting setups. So that was a basic overview of Unity's light mapping and baking systems. Of course, you can go into much more depth into each of these various different options, tweaking them. So I recommend if this is something that interests you and it is something that you are thinking of using for your future projects, do more research into this, as there are many different avenues you can go down when it comes to lighting inside of Unity. So thank you for watching. Hey everyone, in this lesson, we're going to be going over a few different ways that you can optimize your user interfaces inside of Unity, and this will help for both mobile and for pretty much every other single game you create. Now, here in my game that I have just for this course, there isn't a lot of UI. We have our canvas over here, and inside the canvas, we have a button and an end screen, which just has a button and text on it. So when it comes to optimization, this isn't necessary for this type of game, but let's just say you have a game where you have maybe hundreds of buttons, hundreds of text elements, and it's maybe a UI focused game. Well, in that case, having the UI have that many elements, it can slow down performance for a number of different reasons. First of all, one of the most performant impacting factors when it comes to UI is the raycaster. So if I select the canvas right here and go over to the inspector, you'll see that we have a number of different components on our canvas. We have our rect transform, which is basically a transform component for UI elements. We then have canvas, which is in charge of rendering the elements to the canvas and just the overall management of the canvas. The canvas scaler is in charge of changing the aspect ratio and resolution of the canvas, and the graphics raycaster here, which is in charge of detecting inputs from our finger or our mouse when we are clicking on various different UI elements. And this game UI script down here is just part of the game, so we can ignore that. Now, inside of Unity, let's just say you have a canvas which has text only. Maybe you have a canvas that is just there to display the player's scores or just to display the player's HUD elements, and there are no interactions on that canvas. Well, in that case, a graphics raycaster would be not necessary. You don't need to click on anything, and in that case, you should actually remove this component. And the reason why is because even if you don't have any buttons on screen, this graphics raycaster is still going to be using up part of your CPU, checking to see if you are clicking on any of the UI elements. So what we can do is just right click and go remove component. I'm not going to do that since I do need the graphics raycaster for my buttons on the end screen and the next player button right here. But if you do have a canvas that is lacking in buttons or is just there to display information, then you should remove the graphics raycaster. Now, when it comes to canvases, generally when creating your first game, you only really have one canvas. Although as you do later on expand your games and increase the UI in those games, it's recommended that you actually have multiple canvases because think about it. Each time a canvas is active or enabled in this case, it is going to be going through every single child object, checking to see if it needs to be rendered on screen, checking to see if it is active, disabled, and various other things based on how it should show that object. Now, let's just say you have a game which has the player's HUD, the menu, the scoreboard, various different elements in a single canvas. Well, every single frame, it's going to be going through and checking to see each of those if they need to be rendered. It will then render them. Now, the problem with that is if you do have various things such as the scoreboard or pause menu not always active, then it's quite unnecessary to have that in an activated canvas. So instead of having like a pause menu and a scoreboard or a settings screen or a menu screen inside a single canvas along with every other thing in your game, you should split them up into different canvases. So have a canvas for the player's HUD that's always going to be active, have a canvas for the pause menu, have a canvas for the settings menu. Try and segmentate all your various different UI sort of sections into various different canvases so you can disable and enable the canvases rather than the specific UI elements. And that will increase performance in the long run depending on how large your project actually is. So we've gone over canvases. Now, one more thing to do with the graphics raycaster is if we select the button right here, for example, and we go down to the image component, you'll see that there is a raycast target boolean right here, which we can enable or disable. And this is going to determine whether or not this object right here, this component, is going to be detecting raycasts. Now, since this is a button, we do need to have this enabled in order to actually detect clicks. But if I open up my end screen, for example, here, and we go to one of the text elements here, I'm using Text Mesh Pro, you'll see that if we click on the extra settings here, raycast target is also enabled. Now, when working with text elements, that is not necessary. So I can just disable that on all of my text elements right here, disable raycast target, as well as on any pretty much every single UI element that doesn't need to be interacted with the finger or with a mouse click. You can basically disable raycast target. So it'll take that out of the pool of possibilities that the graphic raycast has to go through in order to determine if it's being clicked. So these are just a few small things that can help you out with optimizing your UI, as when it comes down to mobile game development, any sort of performance increase is really great. And eventually you may have a game which is very UI heavy, has lots of UI elements, and in that case, optimizing your UI may be necessary in order to get the performance that you wish. So thank you for watching. Hey everyone, in this lesson we are going to go over a few scripting optimizations to help out with performance. As you create your games and increase the number of scripts and complexity of them, it will potentially get to a point where the scripts are impacting the performance, and this can be due to a number of different reasons. First of all, let's go over the concept of caching objects. So let's just say, for example, you have a game where you want to change the ball's color to a certain color every single frame. Now in this example, inside of the update function, we are finding the ball object, then we are getting the mesh renderer component and changing its color to blue. Now this isn't really a proper game, this is just an example to show off how we can improve this line of code. So we've got this, and in fact this line of code is very inefficient for a number of reasons. First of all, GameObject.find is a very expensive function to call. This basically searches through the entire scene for an object called ball, and then .getComponent is also an expensive function to call as well. And doing this every single frame will definitely impact performance if we do this quite a lot. So how do we fix it? Well, we can fix it by caching the ball's mesh renderer component. Since we are calling this every single frame, it is helpful to cache this to a variable. So as you can see, I've created a private mesh renderer variable called ball mesh renderer. And inside of the awake function, we are setting this to be equal to the GameObject.findBall.getComponent mesh renderer. We are only calling GameObject.find and get component once in the entire game, compared to before, we'd be calling it potentially 60 times a second. Okay, so that's going to greatly increase performance with this set of code. And down in the update function, we are just getting the color of our variable and changing it to blue, which is going to greatly improve our performance as well doing it that way. Now inside of Unity, there are a number of helpful functions such as GameObject.find, which finds an object in the scene, FindObject.type, which finds an object with a specified component, FindObject with tag finds an object of a certain tag, getComponent, and camera.main. These function calls are expensive and they should not really ever be done inside of the update function. They should really only be called once if you can help it to find a single object, then cache that object and just use that variable. Refer to that variable whenever you need to access it then. Camera.main, especially behind the scenes, that's basically just GameObject.find object with tag. It's basically calling that behind the scenes. And generally, when looking at tutorials or how to do something, you would always see camera.main being used. And if you're calling that every single frame, especially for if you want to track the camera to the player, calling that every frame, it is very good if you cache that camera.main into its own variable. Another thing that can help greatly on performance is reducing function calls, okay? Because generally, inside of the update function, you'll be wanting to run certain things such as movement, turning, and all of that. Yeah, it should be done every frame, but there are often things as well that you can call not every single frame. Maybe you want to be constantly checking to see if the player has reached a certain score or if the player has gotten somewhere or reached some sort of objective. In that case, you don't want to be calling it every single frame. Instead, you want to be calling it every 0.2 or 0.1 seconds. If it's not something that is directly tied to the player input, such as moving, looking, shooting, jumping, or anything like that, then you can actually give it a delay. So instead of calling it 60 times a second, you can call it 5 times a second. And again, if it's not an input, this difference is not really going to be noticeable. Some other optimizations are reducing debug.log calls. I know when you want to test out certain things, test out certain functions, if statements, you'll be chucking in debug.log calls constantly. And the problem with that is debug.log is actually quite expensive as well. So I recommend that once you have finished testing it out, that you just remove that from the code, because as well as impacting performance, it also clogs up your console for other important messages. Reducing the frequency of raycasts is also an important factor, as you could imagine, raycasts are quite expensive, as well as using loops in the update function. You've got to be very careful with this one. If you're looping through maybe 4 elements or 5 elements, that's fine, but if you're going up to maybe hundreds of things you're looping through every single frame, that can greatly impact your performance. So do keep in mind how many things you want to loop through every frame, and if you can help it, try and refer back to reducing these function calls here by only calling it a certain amount of times a second compared to every single frame. Okay, and finally, if you're instantiating lots of the same object, such as bullets or particle effects, use object pooling. Now, object pooling is basically the idea of reusing game objects that are all the same. So again, for bullets or for particle effects or for something where you have lots and lots of the exact same object that you want to instantiate and then destroy, you can use object pooling. Because traditionally, instantiating and destroying, they can be quite expensive if you're doing it consistently over a very high frequency. So object pooling, basically at the start of the game, you'll instantiate a large number of these objects, so you'll have a big performance impact for the first frame or so, but apart from that, it should be smooth. And then pretty much instead of instantiating and destroying these game objects, you enable or disable them when you need them and when you don't. Now, there are many methods and systems online and on the asset store that handle object pooling, or you could go ahead and create your own system. So I recommend that you do your research and see what the best method for you will be. So yeah, that is just a few different ways that you can help increase performance with your scripting and optimize various different aspects. So I hope you learned something new, and I'll see you all in the next lesson.